In this video, I'm going to introduce a notation that we use when we're trying to add up a whole bunch of numbers. To see how this works, let a1, a2, up through an be some numbers. Then their sum is written in this compact form. So let's see what this means. This symbol here is the Greek letter sigma, the capital letter sigma, which makes the S sound, and so it stands for sum. And the variable beneath the sigma, this little I, this is called an index. What it does is it tells you where to start and stop the summation. So if I'm looking at this expression here on the left side, it's telling me to sum up the figures a sub I, where I ranges from 1 up to n. And so this is what's happening on the right side here. We just replace this index I with all the values between 1 and n. Okay, this is not very concrete example, so let's look at more concrete ones. This first sum here is the sum of I from I ranging from 1 to 6, which means first we replace I with 1, and that's where we get this term here from. Then we replace it with 2, then we replace it with 3, and so on, up until we get to 6. And we're adding up all of those individual terms. So that's what this expression means. It's a compact way of writing the sum of all the numbers from 1 to 6. This next example, we have the sum of 1 over j plus 1, j ranging from 1 to 6. And again, all we do is we take this full expression here, and we write it 6 times, and replacing j each time with all the numbers from 1 to 6. First we replace j with 1, then we replace j with 2, and so on, up until we've replaced j with 6. And now this is an expression which is compactly written in this form. In this next example, we're including 100 terms to be summed together, so certainly this is a preferable way to write it. But what does it mean? Well, first you replace k with 1 in this expression, square root of 1, then you replace k with 2, and then 3, and so on, up until you get to 100. And so it's the sum of these 100 terms compactly written in this form. And you can have even more complicated expressions if you like, but the procedure is basically the same. This one, the I is ranging from 5 to 50. So we begin by replacing I in this full expression with 5. So 5 squared minus 2 times 5 plus 3. And then you bump it up to 6. 6 squared minus 2 times 6 plus 3, and so on. You add up all these terms up until you've let I equal 50. This is the stopping point in this sum. Now, sometimes it'll be convenient to be able to go from this traditional notation back to sigma notation. And there are often several ways to do this, and the idea is to recognize some pattern among the terms being added together. For instance, here I notice that the denominators are just multiples of 3. So the first sum is 1 over 3 times 1, the second one is 1 over 3 times 2, and then the third 1 over 3 times 3, and so on until we get up to this last one, which is 1 over 3 times 9. And so I see that there's only one little figure in these terms that is changing. So that's a pattern. And so we can rewrite this as 1 over 3 times this index, which seems to be growing. And I is ranging from 1 to 9, as we can see here. Okay, in this next example, let's see what pattern there is. I notice that the denominator in each of these terms is exactly 5 more than the numerator. And so the pattern that I have noticed is written this way. We have 5 over 5 plus 5, 6 over 6 plus 5, 7 over 7 plus 5, and so on. Okay, well then the pattern is that these two numbers agree in each of these terms and are increasing, while this 5 remains constant in each term. And so this number here and here is our index, which grows from 5 to 20. So the way we can write that is this. We replace that number which was growing with this index, and we let the index range from 5 to 20. We could have done this slightly differently. Instead of noticing that the denominator is 5 more than the numerator, we could have just as easily said that the numerator is 5 less than the denominator, which I can write like this. 10 minus 5 over 10 is 5 over 10. 11 minus 5 over 11 is 6 over 11, and so on. But now looking at it this way, I see that these numbers match and are increasing. So this should serve as my index this time. And the index should range from 10 up to 25. And so we write it this way. And so, yes, these two expressions using sigma notation both represent this same sum of these same fractions. So there's often multiple ways to write a sum in sigma notation. Okay, let's do another one. Let's see, what pattern do we have here? The 8 and the 3 seems to be common among all of these expressions, so those will be constants. But then this expression here seems to be growing by 5s each time. And so our index must be included there. Well, let's see, I can write this as 5 times 1, and then 5 times 2, 5 times 3, and so on. And so we see that if I let the index range from 1 up to 8, then my sigma notation could look like this. 5 times your index divided by 8 plus 3, I ranging from 1 to 8. Okay, there are certain properties of summation that we can use to actually evaluate certain sums. For instance, we have the constant multiple rule and the sum rule, just as we did for differentiation and anti-differentiation. So it's important that we realize in this that it really doesn't matter where the index starts and stops for these properties to be true. But here's an example of how it works. For example, here the index starts at 0. That's not a problem, though. We just use the sum rule as normal. The starting and stopping points for the index remain the same as for this original sum. Next, I'm going to use this constant multiple rule to bring the 2 out front. And this is now, well, it may look more complicated, but in fact this is an easier sum to work with. But first, let's see what this actually means in traditional notation. What did this line actually mean? Well, if we just rewrite this in traditional notation, then regroup all the terms that have 2's and all these 1's, group those together, then we see that we can pull out this 2 from all these terms from 0 up to 10, and then rewrite the expression inside the parentheses as sigma notation. That's this one here, this first sum from 0 to 10 of just j. That's the expression inside the parentheses. And then this sum of 1's 11 times, that's exactly this sum here, j equals 0 to 10 of just 1. 1 is just repeated 11 times. And so this is a good and intuitive way of seeing why these two expressions are the same, because all we've done is we've rearranged terms and then we've factored out a 2. Okay, so here are a few summation formulas that are useful when we're trying to evaluate large sums. For this first sum, c is a constant. This is saying that the sum of an expression not depending on the index is just the number of terms in that sum times that constant. This sum here is saying the sum of the positive numbers from 1 to n is equal to n times n plus 1 over 2. This third sum is saying that the sum of the squares of the numbers, the first n squares, is equal to this expression, and the sum of the first n cubes is equal to this expression, and this one is more of a geometric sum. This is a to the 1 plus a squared plus a cubed and so on up to a to the n, and that's equal to this expression here. Important for these summation formulas, the index must start at 1 for these to be correct. Okay, I don't want to prove all of these, but I do want to give you an idea of why some of them are true. This first one was easy, actually. We just interpret it in terms of standard notation, right? What is the sum from 1 to n of c? Well, it's just c added to itself n times, which means that it's just c times n. For the second one, it has a nice proof. Consider this array of dots. There are n plus 1 columns and n rows. And I'm going to ask the question, how many red dots do we see here? Well, on the one hand, it's just half as many dots as there are total. And since there are n times n plus 1 total number of dots, it's just half of that. On the other hand, if we count row by row, there's 1 red dot in the first row, 2 in the second row, 3 in the third row, and so on. So it's just 1 plus 2 plus 3 up to n. And so that is exactly this sum. Okay, I'm going to prove one more. This geometric sum. This has a nice simple proof. First of all, we just write the expression in traditional notation. Next, multiply both sides by a. And I've shifted over the terms a little bit just to be suggestive, right? I'm trying to line up a squared with a squared, a cubed with a cubed, and so on. So this is what's happened when I've multiplied both sides by a. And now what I'm going to do is subtract the second line from the first line. So on the left, I just have 1 minus a times this sum. And on the right side, look what's happening. I have a minus 0 is a squared minus a squared is 0, so that goes away. A cubed minus a cubed goes away. And all the way up to a to the n minus a to the n. All those terms in the middle go away. But then I'm left with 0 minus a to the n plus 1. And so that simplifies quite a bit down to just a minus a to the n plus 1. Okay, then if I simply divide by 1 minus a, which I can do assuming a is not equal to 1, then this is our formula. Okay, those are all well and good. How do we use them? Let's try to compute this sum. The way I'm going to do it is by first writing it in sigma notation. And so how can I write this? Well, I can write it as, well, it's the sum of the odd integers between 1 and 100. And odd integers can usually be written as 2i minus 1. 2i is an even number, subtract 1 from that, you get an odd number. And let's see, did I get the index right? If I let I equal 1, then I get 2 times 1 minus 1, and that is 1, which is the first term of the sum. And if I plug in I equals 50, then I get 2 times 50 is 100, minus 1 is 99, which is the last term in the sum, so this looks right. Okay, now let's use the summation formulas to evaluate this sum. First, I'm going to use the constant multiple rule and the sum rule to split it up into two sums. And next, I'm going to use the summation formulas directly. This first one was the sum of the first 50 whole numbers, and you remember that was 50 times 51 over 2. That was formula 2 I used there. And then this one here is formula 1. This is just a constant being summed up from 1 to 50. So that's that constant, 1 times 50, the number of terms. Okay, well this is now an expression that's easy to evaluate in a calculator. Okay, let's do a similar thing, but this time instead of adding up the odd numbers from 1 to 100, we're going to add up their squares. So we begin by writing it in sigma notation. Again, I'm encoding an odd number as 2i minus 1, and I can double check that the indices are right. I'm starting with 1 squared and I'm ending with 99 squared. But then how do I evaluate this? Well, I'm going to have to rewrite it. I'm going to have to multiply out that binomial. Next, use the sum rule and the constant multiple rule to split up into 3 separate sums. And now for each of these, I have a formula, which I can now use. And these are the formulas again from a few slides back. And we get this expression which we can plug into a calculator. Okay, let's do another one. This time I have an alternating signs sum. What's the pattern here? Let's see, 1 minus 2 plus 4 minus 8. I'm noticing that 2, 4, 8, these are doubling each time, except that I'm also alternating signs. So I'm actually multiplying by -2 from one term to the next. Which means that actually what I'm doing is I'm summing up the terms -2 to the I. -2 to the 0 is 1. -2 to the 1 is -2. -2 squared is +4, and so on. So if I let I range from 0 up to 20, then I've precisely encoded this full sum like this. Okay, well, I wanted to use the formula for a to the I that we did on a few slides back, this sum for a to the I. But remember that formula was only good if this index started at 1. So to fix that, I'm simply going to write down the I equals 0 term here, plus all the other terms from 1 up to 20. This is called running off the first term. Okay, well now that I've done that, this expression here does fit the form of that formula, of that summation formula. So we can now use the formula that we developed there. And now this is an expression that we can plug into a calculator. To recap, sigma notation is just a nice, concise way to write large sums, even if there are many, many terms involved. And if we use certain summation formulas, we can sometimes quickly and easily evaluate complicated-looking sums. And we're going to use this to solve the so-called area problem, which is something I'm going to introduce in the next video. But before we do that, I'd like you to see if you can answer these questions. And bear in mind that you may have multiple possible answers for this second one. Sometimes you can have more than one way of writing a sum in sigma notation. And for this sum here, make sure you are using the properties of summations correctly. For instance, you might need to start by distributing this I. Okay, so try your hand at that, and I will see you in the next video.